So, hello and welcome to this short Grasshopper tutorial on the transform tools. I will do a very quick introduction. This has a little bit the purpose for the other set of tutorials in which we will do animated drawings, and for that I will just do a quick introduction onto how to animate geometry through Grasshopper. So as a kind of first thing, we will just quickly model one or two objects that we then later can use in Grasshopper. For that purpose, you can model really anything, it doesn't really matter. And we are quickly gonna load them as two separate geometries as B-reps. So we say set1 B-rep for the cylinder and set1 B-rep for the cube. A very short tip: if you have to animate a lot of objects, and if you're modeling in Rhino on more complex geometry that you want to continuously update into Grasshopper, one way to go is to use a geometry pipeline. The geometry pipeline essentially takes all the geometry that is in one existing layer, and you can specify which type of geometry it loads automatically into Grasshopper. And the advantage is that if, for instance, we have our cylinder on layer 3 and our cube we keep on layer 5, then through typing in the names here and the geometry, we will have automatically saved the geometry live from Rhino to Grasshopper. So whenever we model now in layer 3, for instance another cube, we will have this geometry automatically loaded into Grasshopper. So this is just a small tip how you can improve your workflow within your animation workflow. So, but now let's look quickly at the different types of transform tools that exist in Grasshopper. We will not go through all of them because only some will be relevant for us for animating. Essentially, they're in many ways similar to what we have as transform tools in Rhino, but there are some small differences and some things that are slightly more precise, so that you can actually set up more complex types of transformations. So what we're going to look at in the transform tab, which is the kind of standard tab in Grasshopper, we will focus primarily on Euclidean transformations and on certain compounding transformations. So we're going to skip morphing, we're going to skip arrays and scaling types because they don't really touch the topic of animating objects in the sense of like moving geometries. This is more relevant if you work parametrically. These tools can become quite handy, but for our purpose now, we will just look at Euclidean and on the last tab for compounding and inversing transformations. So let's start with the very simple thing. Let's move our geometry. With the move component, you need two inputs. So one input is the geometry that we want to move, and the second input, which goes into the connector for T, is a translation vector. So essentially, for vectors, we can literally use multiple ways to define these vectors. We can either define a vector through defining a XYZ vector, so we can simply create a vector with certain properties that moves the object around. That's of course one way to go. Another way to go would be to have a line either from Rhino or generated in some ways in Grasshopper. and to translate this line into vectors. So sometimes you build up certain like kinematic skeletons in Rhino, and you want to use those as kind of basic transform tools in Grasshopper later. So we can load a curve, and we can extract the two endpoints of that curve and generate a vector from that. So now it will be simply moved by the total vector that the curve describes. So as you can see, it's really just, it's completely independent of where the curve is actually lying. Like it wouldn't move the object now from the starting point to the end point, but it's just about moving it along this vector. If we want to move things along curves, we will later look at one transform component that will do these things much easier. So that's linear translation. It's very simple. Like you simply define vectors and how they move. Now, the next kind of transformation we can look at is rotation. There's different types of rotation in Grasshopper. There is rotation along a plane, which I think is the most used or most convenient type of rotation. The inputs here, we have one more input. We have geometry. So again, like what kind of object do we want to move? We have the angle. So of course, when we rotate something, you need an angle. Standard like way of writing the angles is in radians, which I also find more convenient than with angles, but you can also switch this here by right-clicking on the A. You can switch to degrees if you want to rotate in degrees. And bear in mind that it always does the rotation counterclockwise. So if we connect now a slider to this, let's say, and in order to get a good radiant angle, we go with pi. So now we can see that the rotation is from 0 degrees to pi. So like 180 degrees. And it always does it counterclockwise. One other input that is of course in a rotation is the center of rotation. So where does the object actually rotate around? And for this, in this specific component, in the rotate object in a plane, we define a plane around which the object rotates. So in this case now the default is the world XY plane, but we can actually literally define any plane. For instance, we can simply set a point. We can load this point into Grasshopper, and we can create a new plane, for instance, like a YZ plane, in that point. And then if we rotate that object, it would rotate the object around the YZ plane. So here it's important where the center of rotation is, and the orientation of the rotation plane in relation to the object. So unlike the vector, the translation component, it is important you have an input that again is specific to the relationship in space to the object that you want to move. Now, for most purposes, you will use this component for rotating objects, but of course there's also a few other components, for instance, rotate 3D, which essentially is like this component. The rotate around axis is essentially similar to our rotate around the plane component, in that you define again the geometry, you define a center of rotation. Let's take our points that we had before. And you have again an angle. Let's take our same angle. And you have an axis of rotation. Now the axis of rotation essentially creates, if you have a center point and an axis of rotation, what it will generate inside the component is nothing else than a normal plane at that point. So if we, for instance, take we have here currently an YZ plane, so the normal vector of the YZ plane is an X vector. So now our rotation of these two objects is identical because it essentially builds up the same requirements for the rotation. Why necessarily using this instead of that? I think it might depend on the specific setup you want to work with. I tend to find this a bit easier because you simply define planes. Sometimes it might be have an advantage to use that component instead. Another way is to define it by a curve. So in this case, you again have the geometry. We give an angle that it should move around, and you define it by a curve axis. So in our case, we have our curve that we have defined here. So let's use this one. And it will use this curve as the kind of rotation axis. Now, the way it works with the curve is it simply takes the starting point as the center of rotation, and it uses the direction of the vector as the normal vector of that curve. So if I flip this curve in Rhino, it will also flip the rotation direction of the object. So, this is about rotation. There's one more component, but I think you can test it for yourself. This is not so important. And the third kind of transformation tool that we will look at is Orient. Orient is kind of a very practical tool because sometimes when you animate or when you have a complex kinematic chain where you have a lot of objects that need to move in a sequence of certain motions, it is quite heavy for the geometry to be transformed all the way through. And it makes sense to actually just animate planes and then just reference your geometry to this last animated plane. It will make your files much lighter and it will simplify your scripts immensely. So what we're going to do here is we're going to have again an input for our geometry, and we will test this now with one of our transform tools that we already put out here. So let's take the rotation of a plane, and instead of the geometry that we are going to transform, copy this maybe, we will use a specific plane, a new specific plane that we create. Let's say we build up a plane here. From that point, let's point in, and we create a XY plane. So now we have our XY plane in Rhino here, and we are rotating this plane around our other YZ plane, which we have here. So maybe I'll turn off for a second all this other geometry and the input geometries. So we have our plane which we want to rotate. We have the plane through which the other one is rotated, and the green one in the Rhino viewport now is the result of this rotation. So now the question is, okay, how do we attach now our object to this? And this is where the Orient component comes into play. We have our box, which kind of sits nicely on the XY world plane, and we're going to use that immediately to reference the object from one plane to the other. So what the Orient tool does, similar to how it works in Rhino, is you define the geometry, you define a reference plane. So in our case, we simply take the XY world plane, which is our plane also of the Rhino coordinate system, and we reference it to our newly animated plane. Sorry, and we're gonna use our cube instead of the cylinder this time. So now you can see that our our transformation, the object actually doesn't start where the object is modeled, because the object is modeled on the XY world coordinate system, and because the initial transformation is a plane that is already somewhere else, which is out here. So the object in the initial kind of animated position is already somewhere else, and then it's being animated along this rotation through which we animated our plane. So this way you can actually animate easier by setting up your planes, how they are animated through, and then continuously model your components that you want to move separately in XY world, and then just simply at the very last step transform them through the Orient component. Now, if you have multiple transformations that one object should run through, there is a way to actually connect them. So one way would be, for instance, if we have our, if we take, for instance, our moved, quickly hide this too. If we have our moved cylinder, so this is our cylinder which is executing a linear movement. Maybe let's, for the purpose of the tutorial, make it a little bit stronger movement. So now it moves 50 meters away. And then we have the movement, the rotation of that object. So that's kind of our second movement. And now we say we want this object to transform, to execute both of these transformations at once. We want to both rotate and move it. So one way to go about this is to simply not use this geometry as the geometry for moving, but immediately the first, the geometry that was first rotated. So in that sense, you can specify rotation, and then you can move the object. So if we hide just a rotated object, we will have the translation of the object, but the translation of the object is based on the rotation first, because the object first rotates and then it translates. This is generally something important with transformations, that they have a hierarchy in which sequence they execute their types of motion. But there's actually if you have quite a complex transformation, if you have a robotic arm, or you have more complex mechanisms, this kind of workflow where you simply transform from one component to the other is not very useful, especially if you have multiple geometries that attach to these things. So similar what I explained before about using simply planes to do transformations. There is a workflow how to specify separate motions and then compound them. This is kind of the term in Grasshopper, them together into one type of transformation. So what we're going to do is we're going to plug this back in here, and when you see the output of each of these transform components, there is always the geometry output, and then there is the transformation. The transformation data is essentially a matrix, and these matrices essentially can be added. Like you can do additions of these different transformation matrices, and you don't have to go deeply into matrix calculations. You simply use the compound component to compound two types of transformations. So now here the output is again a transformation, which essentially combines those two separate transformations. Now, if we want to see the transformation, the final transformation of our object, we need to use a component called simply transform. And what it does is you put in the geometry in the geometry connector, and then in the transform connector you simply plug in the compounded transformation. You could also use this sometimes if you have multiple geometries and you want to use the same kind of transformation for the other geometries. You can simply use the output from the transform data from one component and plug it in here. Or if you have compounded transformations, you need to use this component in order to animate the final object. And now we can see, if I turn off the separate motion, the motion, the kind of control over this object is now through these two sliders, one which controls the X translation and the other which controls the rotation of the object. But that happens through like one component instead of translating through a series of objects. And if you want to inverse a transformation, you can also do that. So you could inverse that entire transformation, and suddenly it literally moves into the opposite direction and rotates around the opposite axis. This is sometimes very practical if you want to switch. Again, if you have a kinematic chain where you have a relationship between different motions of objects and you want to freeze one object and inverse the rotation of the others, with this component you can very quickly view the transformation of the other objects in relation to that. So another component that might be useful is simply the split component, which returns you the separate types of motion again into the compounded motions into a list of separate motions. So if you want to take apart your different types of transformations that you have compounded along a more complex model, you can subdivide them again into their separate parts. Yeah, and that's basically it for the basics. If you you can of course play around with these different types of transformations. We didn't look at mirroring. Mirroring is also a Euclidean transformation which has the same kind of outputs for compounding and inverting, but because it essentially mirrors the object, it's not a real transformation that an object could execute in real life. We didn't look at it specifically, but also all these scaling operations, they work on the same principle as the basic transformations that you can compound and merge these different types of transformations into one.